What we're talking about here is types of collisions. Last time we discussed an inelastic collision. An inelastic collision, this guy over here, is one in which only the momentum is conserved. So this type of collision happens and occurs when you have one object that's moving and another object might be moving. Maybe it's even moving in this opposite direction and they're coming in for a collision. So you have one mass and you have another mass and they're both moving towards each other, and then what happens is the two of them stick together and that whole thing goes off with some velocity, where this is mass 1 plus mass 2. They're stuck together. What happens in an inelastic collision, of course your system total momentum is conserved. Sorry, I apologize if the audio went out, so I'll just repeat it. In an inelastic collision, only the momentum is conserved. So the total momentum of the system before the collision is equal to the momentum after the collision, and we know that already. We've learned that. But the thing also about an inelastic collision is that the kinetic energy after the collision is always going to be less. So here we have some total kinetic energy before, and you could calculate that as 1/2 mass 1 v1 squared plus 1/2 mass 2 v2 squared. So in other words, you take the kinetic energy of this to the kinetic energy of that, get the total kinetic energy before. After your total kinetic energy is going to be 1/2. Now the whole mass is going to be moving as one. So we got m1 plus m2 for our new mass, and that at some final velocity here, v squared. Well, with an inelastic collision, this number is going to be less than this number. So with an inelastic collision, the final kinetic energy, which is the kinetic energy of your system now, after the collision, is always going to be less than what you started out with. And that's because when two objects collide, they make noise, so sound. You have a sound. There might be some heat generated when they're colliding. They're colliding in like that, and there's some sound because they're colliding. There's some heat given off. There's some deforming of the two objects, some deformation. Maybe, and so there might even be some joining of, or bonding of one material to the other. So all of these things require energy. They require energy. And we didn't talk about things like sound yet in our course, but sound is energy. And so if it's giving off a sound, it certainly is giving off energy. And so the energy after these two things collide is not going to quite be the same as the energy of the system before they collide, because the sum of the energy that the system had before is going to go into things like sound, heat, and deformation. So it's going to lose this amount of energy in the process of sticking together. So with an inelastic collision, the kinetic energy afterward, after the collision, is always going to be less than the kinetic energy that you started with. Not of the individual particles or the individual objects, but of the entire system as a whole, just like we did with momentum. Here the total kinetic energy is the sum of all the kinetic energies of all the interacting parts. Before they collide, you have some total K initial. After collision, you have some K final. And what we're saying is that the final kinetic energy is less than the initial. That's for an inelastic collision. Let's talk a little bit about an elastic collision. In an elastic collision, not only is the momentum conserved, but also the kinetic energy is conserved as well. And an elastic collision, for our purposes, what we want to say is that you have complete Well, we've got bounce back, no sound. We're going to assume there's no sound in the interaction, no heat given off, no deformation, whatever. When these two guys touch, so we got one moving that way, one moving this way. Let's say that's mass 1 and mass 2. So we have a kinetic energy before, which is 1/2 mass 1 V1, if this is V1, and V2 squared, plus 1/2 mass 2 V2 squared. This is the kinetic energy initial for our elastic collision, because what's going to happen in an elastic collision is that when they meet, you're going to assume that the materials give in, like elastic, like a spring compression, and then that they completely go back to their original form, and so you might have some energy being stored as potential energy in the interaction when they're interacting with each other, but that quickly returns to kinetic energy after, and now we might have some different velocities where we have our masses sitting like this and they're moving in different directions here after the collision. So our kinetic energy then, this is our final kinetic energy, would be the kinetic energy of this one plus this one. That final kinetic energy and our initial kinetic energy will be equal. So what we have to say about elastic now, so for elastic collisions, our kinetic energy of our system, the total kinetic energy before the collision, will be equal to the kinetic energy after the collision. That's only for perfectly elastic collisions, which in principle may not exist because you're always going to have some energy loss when things collide. But for purposes of physics and what we're talking about, let's assume in this book, and what we're talking about for our purposes when we talk about elastic collisions, we're going to assume that no kinetic energy is lost. So we have the conservation of kinetic energy, in addition to, of course, the conservation of momentum. So what we're going to do is we're going to do a problem to illustrate this now very, very quickly if I can. I'm going to try and do it quickly anyway. Let's see. All right. So let's do one from the book. We can do it really quickly. This is on page 211, and I'm going to do the sample problem first. This is page 210. We have a marble, and it is 0.015 kilograms. It's moving to the right. That's this direction at a velocity of 0.225 meters per second. And it has an elastic head-on collision with a shooter marble, which is a little bit bigger guy here, which has a mass of 0.03 kilograms. And that guy is moving this direction with a speed or velocity of 0.18 meters per second. And then you have a collision here, see? And then after the collision, so this is before, and then after, we're going to have this situation where the smaller marble moves to the left. So now the smaller marble is moving this way with a speed of 0.315 meters per second. This here is the 0.015 marble. And we assume that there's no rotations. Everything's just sliding along on a frictionless surface. And we want to know what is the velocity. So we still have this guy here, 0.03 kilograms, and we're not sure what this velocity is over here. In fact, we're not sure whether it goes this way or the other way. So let's assume that it goes to the right. We're not sure, but let's just assume that it's going to go to the right. How can we figure that out? Well, let's look at conservation of momentum. This is a perfectly elastic collision, so no kinetic energy is lost. The two guys bounce back, and they're going their own separate ways with different velocities after the collision. So the total momentum before the collision is going to be the mass times the velocity of each one added together. This is going to be a mass of 0.03. Notice that I put a negative for this velocity here because it's going the opposite direction. I'm going to assume that this way is positive for now. And then we've got 0.015 on this side. We know it's going to the left with this velocity, and we are going to have 0.03 kilograms. Some velocity, we're not sure, but we know the two are going to be equal together. When you do all of the math here and you multiply these things together, and then you bring this guy over and subtract and do all that kind of math, which I'm not going to do right here for you, you're going to find that the velocity is, according to the calculations in the book, 0.09, yeah, meters, that's a 9.09 meters per second to the right, because it's positive. So we know it's moving in this direction, so our initial guess that it moves this way was correct. Now, knowing that, we could double check ourselves, because we know if we have a perfectly elastic collision, the kinetic energy will be the same before and after. So what's the kinetic energy before the collision? Well, we have 1/2 the mass times the velocity here squared, plus the kinetic energy of this guy, which is 1/2 0.03 times 0.18 squared. Now this is a negative, but it's squared, so it's not going to matter. That has to be equal to 1/2 this mass, which is 0.015, times this new velocity of negative 0.315 squared, plus 1/2 0.03 times this new velocity, which we calculated to be 0.09 squared. And the question is, and I'll leave this for you to solve, are they equal? Is this side equal to this side? And if you do that math, you should find that yes, they are in fact equal, and both sides will give you the same number. This is 8.7 times 10 to the negative 4 joules, and this side is also 8.7 times 10 to the negative 4 joules. So we had complete conservation of kinetic energy. And I hope that helped, and we'll talk more later.